All right, we're going to start now on number 11, and this one's going to focus a little more on linear functions from rates of change. So we're told that gas stations in the U.S. Dispense gas at a rate of 10 gallons per minute, and that's an absolute change. Every minute that goes by, 10 more gallons are put into your car. And so we're going to use that piece of information to answer a few questions. So in this first one, we're told that we arrive at the gas station and we already have 5 gallons of gas in our car, and we only pump gas for 30 seconds. And how much gas did you have in your tank when you stopped pumping? So I know I started with 5 gallons. So I'm going to say, okay, I have 5 gallons. And then for every minute that goes by, 10 more gallons get put into my car. So I could take my rate and times it by basically the length of time I pumped gas for. But I only pumped gas for half a minute, not even a full minute. So I have those 5 initial gallons I put in, plus what ends up being 5 more gallons, because if I pump 10 gallons in a full minute, in half a minute, I'm only going to be pumping half of that amount, 5. And so 5 plus 5 would mean I would end with 10 gallons of gas in my car. Now, part B is asking us to work backwards. It's saying, okay, our car holds 13.5 gallons of gas, and we're starting with those same 5 gallons, and I want to know how long is it going to take to fill up my tank with gas. So I know that I started with 5, and that 10 times the time in minutes will tell me how much gas gets put in total, and I want that to end up being 13.5 gallons. So I'm creating sort of like an equation that I can solve. Now, if I subtract 5 from 13.5, I know that I need to figure out how long it's going to take me to get 8.5 gallons into my tank, and I'm told that it's 10 gallons, per minute. So, and if I divide both sides by 10, I would get time equals basically 0.85. Now that's minutes. That doesn't mean a lot to me. So if I wanted to turn that into seconds, I would need to multiply 0.85 by 60, and I should get around 51 seconds. That's one way to go about doing this. I find the equation just as helpful to me, and it actually comes back later on. Now, part C, we already sort of answered when we were talking about it before we began. It asked, is this an absolute change or a relative change? And it's an absolute change because basically you're adding a constant amount of gas every minute. And so in it being an additive relationship, we're looking at an absolute change. And last but not least, they're asking us to write a function. So given that 10 gallons per minute and starting with 5 gallons, can we come up with a function that would tell us how, given a certain amount of time, how much gas would we have in our car? And so I'm going to make G the gallons of gas in car, and T is the number of minutes pumping gas. And this is a linear function. This right here is my slope, and that 5 gallons is my initial value. So I know G of T equals the 5 gallons I started with plus 10 times my time. So we see we can label some stuff. That we got our initial value, and 10 right here would be our slope, or our rate of change, our average rate of change, our constant rate of change in this case. And then T was our number of minutes pumping gas, and G was our gallons of gas in the car. All right, number 12. So number 12, we are given that leasing a car, you need $800 for a down payment. So a down payment's going to be like an initial value. And then we're told we also have a $240 fee processing, or a sort of $240 we'd have to pay per month. So this is our rate. And since it's a pay per month, it's additive, which means it's an absolute change. So we're looking at a linear function. So if I write a linear function, I'm going to have sort of the cost. So let's make cost of leasing a car C. So C of X equals my initial value, 800, plus 240x, where x is the number of months, and C is our cost of leasing the car. So B then's asking, okay, how long would I be able to lease this car if I only have $3,680 to put towards my car? And so I can create an equation, 3,680 equals 800 plus 240x, and use this and solve for x. And I'm going to let you go through the algebra. And if you do, you should wind up with x comes out to be 12 months. All right, so on both of those past two problems, we were looking and focused on linear functions. On this next one, we're going to sort of be using data and going sort of back to what we were doing at the beginning with some absolute changes, relative changes, average rates of change, so going back to our types of change. And then at the end, thinking about sort of what function do we think would be the better one to use to describe this situation. So remember, absolute change. So we're looking here for an absolute change between 25.5 months and 5.5 months. So I'm going to just highlight those two values on my table here. So I have this one and this one. All right, so the new data would be the 12.9, what it is at 25.5 months, and we'd minus that from 7.6, which was the weight at 5.5 months. And so we get an absolute change of 5.3 kilograms of increased weight over those 20 months. Now, if I want to turn this into an average rate of change, I would take that absolute change, so the absolute change, and divide it by my change in time. So in this case, that would be the 5.3 kilograms divided by, well, 20 months have gone by. So I'm going to divide by 20. And so I would see that the average infant puts on 0.265 kilograms per month during those first 20 months. And this would be the case like if I was sort of graphing with a linear function, so it comes out to be a line. Okay, sort of makes sense. Now, if I change gears here and I'm looking for the relative change, remember a relative change is a percent, where I take my absolute change, that 12.9 minus 7.6, and I'm going to divide it by the sort of original weight, and I end up with the percent of 69.7%. So our baby's weight increases 69.7% from where it started over those 20 months. Now, if I want to figure out the percent increase each month, now I need to do something a little different. So there's a few options here. One option is that I take my end value, the 12.9, and I take my start value and divide it by 7.6, and I'm going to raise all of that to the 1/20th power, and then I need to minus out 100%, and that would get me 2.7% growth. That's one option to figure out the percent increase. Another option would be to use Desmos to sort of come up and sort of model an exponential function between these 2 points, and I will show that in a different video. For now, I just sort of am going to show you the formula. And then the last question is like, what do you think? Looking at this data, do you think an exponential function or a linear function would be better? And the choice is sort of up to you. I notice here, okay, initially I'm going up by 3, but then I'm only going up sort of by 2, then it's even less than 2, now it's like 1. So my rate doesn't seem constant. This last one's less than 1. So since my rate of change is changing, I'm probably not going to go with a linear function as the best. I would argue that probably is a better model to use an exponential function. And my explanation would be that the rate of change between my various data points in the table doesn't really seem to be constant. So I'm not going to keep assuming that, the weight's going to keep going up that same amount each month. It seems to sort of be petering off. Hopefully this helps you get started on this practice assignment, and we'll keep working with linear functions and exponential functions over the coming class periods.